Welcome back, folks. Today we're going to get into lesson 5.2, analyzing functions with the second derivative. Now, our previous lesson, 5.1, was all about what the first derivative of a function told us. Again, from that we could find intervals of increasing, decreasing, identify local mins and maxes. Okay, with these next two kind of parts, 5.2, we're going to look at the second derivative. Part 1 we'll talk about concavity and inflection points, and then part 2 we'll get into the second derivative test. So here we go. Now when we say concavity, we're talking about a way to describe the shape of the graph of a function. And functions can either be concave up or concave down. Now concave up being where the graph opens up like a U. You can think about it as if we poured some water into this graph, the concave up graph would hold it. Whereas concave down is the graph opening down an upside down U shape, okay, where it would spill out if I try to fill water into this portion of the graph. And what we're going to do is we're going to look at how the second derivative of our functions relate to concavity. Okay, we had exercise 5.2 online, meant to help you get kind of an intuitive feel for how the derivative, second derivative relate to concavity. So if you haven't done that yet, pause this video, go ahead and work through those slides quick. But anyways, what we're going to see when our graph is concave up, and I look at tangent lines to that graph, okay, where the slope of the tangent line is the value of the derivative, what I see here is that slope is increasing as I move through it. It starts negative here, and then it's less negative, less negative. At some point it's going to flip over to positive, and that's going to increase till I get to this point of inflection here. Okay, so for that reason, a graph is concave up on an interval when the second derivative, okay, the rate of change of the slope of the graph, is greater than 0, or in other words, positive on that interval. All right, same idea with when a graph is concave down. If I look at some tangent lines, with again the slope of those tangent lines being the value of the derivative, what I see here is that those slopes start positive, they become less and less and less until they turn negative eventually. Okay, so if the slopes are decreasing, that means the second derivative is negative. Okay, so the graph of f is concave down on an interval when f prime, double prime is less than 0 on that interval. So in other words, when that second derivative is less than 0. Okay, so we can determine the concavity on intervals by looking at the values of the second derivatives. Now one more thing here, we'll talk about the point of inflection, okay, where our graph flips from either concave up to down or vice versa. And we'll say that the point P is a point of inflection of f when the graph changes its concavity at P. I should say if right here, the graph changes concavity at P. Okay, so since we switch from concave up to concave down, at this point I'd call that a point of inflection. All right, so let's go ahead and start identifying concavity and points of inflection. Problem 1, identify the intervals on which the function is concave up, concave down, and any points of inflection. Okay, so part A, we have our function, okay, just a polynomial. And for concavity and points of inflection, we want to look at the second derivative. So we'll go ahead and find f prime of x first. Now, if you want some derivative practice, just using the power rule for these first ones, feel free to pause the video and find that first and second derivative. Okay, otherwise, ripping through these quick, we would have a negative 4x to the third plus 12x minus 2 for my first derivative. And then just applying that power rule again for the second, we'd have a negative 12x squared plus a 12, okay, for that second derivative. All right, why do we want the second derivative? Well, we want to know where it is positive, where it's negative, and then where it switches over for our points of inflection. So what we'll do is we'll start off by figuring out where this derivative is equal to 0. Kind of like finding the critical points using a first derivative, the zeros of my second derivative are going to give me the potential points of inflection and flips over in concavity. All right, simple equation to solve. I'm going to subtract 12 on both sides. That'll give me a negative 12x squared is equal to negative 12. Divide both sides by negative 12, and that'll give us an x squared is equal to 1. And then take a square root, and we end up with x is equal to, plus or minus, don't forget that, 1. All right, so that's going to be where my second derivative is equal to 0. Okay, so that's where it's equal to 0. That's where we'll have potential points of inflection, and that's where potentially this graph could flip concavity. All right, so let's go ahead and make a sign chart for this derivative. So we're looking at f double prime of x, and we want to figure out on the number line what intervals. Let's see if we can draw a little straighter line here. Slightly better, there we go. What intervals our second derivative is positive and negative? So we know it's going to be equal to 0 and negative 1 and 1. Now, two ways we could do this. We could go ahead and test points, such as plotting the points negative 2. We could throw a 0 in here and a 2. That wouldn't be too bad. Or, since I know this derivative is just going to be a negative quadratic, looking at this first term, I know it's going to have that upside down parabola shape. Which, as far as where's that above and below 0, it's going to be greater than 0 between negative 1 and 1, and then less than 0 below negative 1, and less than 0 above negative 1. Okay, so again, you can plot points, or if you have something simple you can graph quickly, you just throw the graph up there. All right, once we know what the signs of our second derivative are and where they change, we can figure out concavity. We know this graph is going to be concave up when the second derivative is positive. That's going to happen between negative 1 and 1 here. And then it'll be concave down when that second derivative is negative, which will happen below negative 1. So we could say negative infinity to negative 1. All right, and above 1, 1 to infinity. All right, last thing then, we want to identify the points of inflection. And for this graph, since it does, or for this function, since it does flip from concave down to up at negative 1, and then from concave up to down at 1, it changes concavity. I know I'm going to have points of inflection at x equals negative 1 and 1. Okay, so that would be the where question. We want to identify the points, so let's go ahead and find the y values as well. Here what we'll do is we'll look at f of negative 1. Okay, and that's going to be going back to this original f of x. That'll be a negative 1 to the 4th, okay, plus 6 times negative 1 squared minus 2 times negative 1 minus 3. Okay, so a little power arithmetic here. I've got negative 1, 5, plus 2 more is 7, minus 3 would be a 4. All right, so f of negative 1 is 4, meaning I've got a point of inflection at negative 1, 4. And then we can do the same thing for our other 0 of that second derivative. Okay, the 1. So we have a negative 1 to the 4th plus 6 times 1 squared minus 2 times 1 minus 3. So negative 1, 5, minus 2 is 3, minus 3 is 0. Okay, so meaning that f of 1 is 0, so that other point of inflection is 1, 0. Now, like we said, this would typically be a non-calculator problem on a test or a quiz, but it's not a bad idea once you actually come up with your answer, or if you're struggling to find that answer on homework or practice problems, pull out a calculator and graph the function you're looking at. So I've got our original function graphed here, and let's take a look. Yep, we said it was concave up from -1 to 1, which looks like it's true. It's opening up between 1 and -1 here. Concave down below -1 and above +1. Yep, and then for points of inflection where it switches concavities, I'd say -1, 4 looks like about that point where our derivative is going to go from decreasing back up to increasing again. And then same thing, 1, 0, that makes sense for a point of concavity. All right, so there's a simple example of finding concavity and inflection points. Part B is pretty much the same thing. Why don't you take a minute, pause the video, run through part B, and then hit play to check your answer. All right, part C, let's take a look at another example. And here's one where things don't quite work out the way we expect maybe. Okay, concavity, points of inflection, that's a second derivative question. So we'll find h prime of x, which will be a x to the third minus 12x squared plus 48x. And we'll find the second derivative, h double prime of x, will be equal to a 3x squared minus 24x plus 48. And again, to answer questions about concavity and inflection points, we need to figure out what the signs of our second derivative. So let's start off by figuring out where it's equal to 0. So I'm going to set 3x squared minus 24x plus 48 equal to 0. Now, hopefully this guy factors. Let's pull 3 out of everything to make life a little easier. And that will factor, we can factor that as x minus 4 times x minus 4. Okay, so that potential point of inflection flip on concavity then would just be x equals 4 for this one. And notice with this one, I've got a 0 that shows up twice, a 0 with a multiplicity of 2. So as far as graphs of my second derivative, we know we're going to have a bounce at that 0. Okay, that should tip me off that this one might not work out quite the way the other ones did. So let's take a look. Let's make a sign chart for h double prime of x. And again, its only 0 is the 4. Okay, so we could, with this, plot some points. I could plot a 0 would be nice, and a 5 would be a bit of a pain to do, but doable. If I plug a 0 into this function, we'll get a 48, which is positive. If I plugged a 5 in, what would we have? Well, we'd have a 48 plus a 75 minus a 73. I'm not going to do that math in my head, but I know that's positive as well. As far as a graph of what this h double prime is going to look like, well, that's a positive parabola, so opening up, with a 0 of a multiplicity of 2, so we know what would happen is we'd have a bounce at that 4. That's another way we could think about that. Either way, what we see is that this second derivative is always greater than or equal to 0. So as far as concavity goes, we'll say it is concave up. Whoops. It's concave up on all real numbers. So concave up from -infinity to infinity. Okay, never concave down. And then since it's never flipping concavity, there's no inflection point. Okay, so again, just like with our critical values on the first derivatives, that's where our graph could have mins and maxes. Same idea here, these zeros of the second derivative will be the potential inflection points, but in this case, since we didn't flip concavity, we're never going to get one of those. And when I go ahead and pull up a graph of this guy with an adjusted window, what we're seeing is that it's always opening up. Okay, it never switches concavity, so no points of inflection. So there's an example where things kind of work out nicely the whole time. All right, we're going to finish up by looking at a couple examples that are not polynomials. Okay, polynomials are great kind of simple functions to get a feel for how things like mins, maximums, concavity works. But we also want to be able to find those for any other type of function we know how to find the derivative of. Okay, so same thing here. We have f of x is equal to the 1/3 power, third root in other words. Okay, this one's all set up to derive, so let's find our first derivative first. And again, if you want some derivative practice, feel free, pause the video. Okay, try to find these first and second derivatives. Okay, using my power rule, we'd have a 1/3 out front times the x minus 2 to the 1/3 minus 1. In other words, 1/3 minus 3/3 is going to be negative 2/3. Now with this one, we technically are using the chain rule since there is an inner function, but the derivative of my inner function, my x minus 2, is just a 1. We can ignore that. And then let's find the second derivative. F double prime of x will be equal to, multiplying by my power, negative 2/3 times 1/3 would be a negative 2/9 times that x minus 2 to the negative 2/3 minus 1 would be a negative 5/3. All right, chain rule again, we'd have a 1 for that inner function, so nothing to worry about there. Okay, so there's my second derivative, but I'm not a fan of trying to solve or plug things in with rational exponents. Let's rewrite that in radical form. We can say this second derivative is equal to a negative 2 on top, 9 on the bottom, and this negative 5/3 power we'll put on the bottom. We can write that as the third root of the x minus 2 to the 5th power. All right, so there's my second derivative. Now, when looking for where the concavity flips over, and then also where potential points of inflections are, two things we want to look for. Number one, we want to figure out where that second derivative is equal to 0. Now in this case, since we have a fraction, the zeros are going to come from the numerator. With this 2 here, there's not any x values that are going to make this 0. So there's no values that make my second derivative 0. What we also want to look for there is spots where the function is not differentiable. In other words, where the second derivative is undefined. And for that, what we'll do is we'll look at our denominator and find where that's equal to 0, where we'd have division by 0 issues. All right, so we'll set the denominator equal to 0. Okay, it looks messy, but pretty simple to solve. You could think of kind of undoing the left side. Okay, if I divide both sides by 9, raise the third power, take a 5th root. If I do all that to 0, nothing happens to the 0. So in other words, we're just looking at where this x minus 2 equals 0. Okay, so x equals 2 is a spot where our derivative, our second derivative, is undefined. So that's going to be a potential point of inflection. Let's go ahead and make a sign chart for f double prime. Now for this one, I have no clue what this function is going to look like off the top of my head, so I can't cheat and just sketch a curve. We're actually going to have to test some values. Easiest values I can think of here is we could just do a 0 and see what happens with that. We'll look at f double prime of 0, which would be the negative 2 over 9 third root of 0 minus 2 to the 5th. And that's kind of a mess, but really what I'm worried about is just the sign of this function. Okay, is it positive or negative? So let's say this negative goes along with a 2. We'll throw that up top. And then for the bottom, since 0 minus 2 is negative, that's a negative 2, I know that when I raise that to the 5th power, I'll get a negative out. When I take the third root of a negative, I get a negative out. Okay, when I multiply a negative by 9, I get a negative. In other words, we'll be negative on the bottom. Okay, I'm not worried about what the third root of negative 2 to the 5th is actually equal to. We could find it, but we don't need it. Negative over negative is a positive, okay, meaning that our second derivative is positive on the left side of 2. And then we can do the same thing with another point, such as above 2, probably easiest number to go with will be a 3. We can look at f double prime of 3. So negative 2 over the 9 third root of 3 minus 2 to the 5th. We'll connect this negative with the numerator once again. And then for the denominator, I know that 3 minus 2 is positive. Okay, so when I take a positive number, raise it to the 5th root, take the third root of the 5th power, take the third root of that, multiply it by a 9. We know we're just going to get a positive result. All right, so negative over positive is negative, meaning that my function here is, my second derivative function is negative on the right side of 2. All right, so as far as concavity goes then, we know it's going to be concave up, where that second derivative is positive, so everything below 2, negative infinity to 2, in other words. It'll be concave down for everything above 2, where that second derivative is negative. And then for the points of inflection, okay, this function did switch concavity at 2. Okay, so again, that's a potential point of inflection. It does work. It's going to have a value of 2 comma, and then we can look at the original f of 2 to find the y value. Going back up here, that's just going to be the third root of 2 minus 2, which is just a third root of 0. 0, which is a 0. All right, so 2, 0 is going to be our point of inflection. And then once again, we can graph our original function here with some funnier looking stuff like this. Not a bad idea to actually plug that in and take a look at what it looks like. Yep, what we're seeing is that our graph is opening up on the left side of 2, opening down on the right side, and it looks like at that 2, 0 is where it flips from opening up to opening down. Okay, we'd say the graph is not differentiable at this point. Okay, we'd have a vertical tangent line, okay, but that still acts as a point of inflection. All right, part E is another similar question. Works out slightly differently though. Want you once again pause this video, take a minute, find those derivatives, determine the signs of the second derivative, okay, figure out concavity and points of inflection, hit play to check your answer and see how you did with it.